morning, friends. We are working towards building longitudinal perturbed equations of motion. Okay, and in that we have seen that we only consider motion along x for fx minus mg theta cos theta 1 equal to mu dot was one equation, and there was fz minus mg theta sin theta 1 is equal to m w dot minus q u1 and m is equal to I y q dot. Sometime I may be using f(a)x, as long as they are small letters f(x), f(z) and small m. We all understand these are perturbed aerodynamic force along x direction, body x direction, fz along body z direction, and m is about body y axis. But we are also clear that we are using stability axis system, right, as the body fixed axis system, which is designed in such a way the orientation of x is towards the velocity vector in the vertical plane, right. We are talking about only longitudinal perturbed equations of motion. Perturbed equations of motion. Why we are doing all this thing? Why are taking so much of pain? Because we know that this u, which is u dot here, q, then w, which is w dot here, q dot here, these are all perturbed quantities. So, we will be tracking those perturbed quantities to comment on whether the aircraft is dynamically stable or not, right. That is our purpose. To solve these equations, I need to know what is the dependence of perturbed aerodynamic forces fx, fz and moment on motion variables, their rates or control variables. So, for that what we did, we started writing fx, the function of without fx, we have assumed that it is a function of let us say u by u1 alpha and delta E. That means we have neglected the contribution of alpha dot and q on fx, right. So, what is the message here is we have neglected the contribution of alpha dot and q on perturbed aerodynamic force fx, right. This should be very, very clear. Now, from there what we did, we say now we can write it like this. D alpha into alpha plus df xa by d delta E into delta E. Also, my apology, sometime I may be using f(a)x instead of f(xa). So, both are same thing. So, you have to be patient with me on, sometime I will be using notations which I often forget. Okay. But as long as you understand what is the meaning of dfxa by du by u1, this is the partial derivative, how much the force along x is changing per unit change in u by u1. Similarly, for alpha and delta E. And we have also found out dfxa by du by u1, and the expression was minus q1 s 2 cd1 plus cdu. Similarly, of course, at steady state, because at steady state I am using the term 1 here, right. And what is the steady state for our case? It is the cruise, right. Similarly, dfxa by d alpha we found it to be Q1s minus CD alpha plus CL1. And similarly, dfxa by d delta E was found to be minus Q1 S CD delta E. CD alpha, you know what is. When I say CD, that's a drag polar I represent, CD naught plus KCL square. So I can easily find out dCD by d alpha for small angle, but we'll assume that CD naught doesn't depend upon alpha. And I can take a derivative, and we have shown what will be the approximate expression for CD alpha. And also you know what is CL1. CL1 is the CL to maintain cruise, level cruise at a given altitude. And given altitude and given speed at steady state is the Q1. That is, Q1 is at cruise, what is the dynamic pressure? Dynamic pressure. Once I know this, it is so straightforward for us. What I have to do, we'll take the first equation fx and see how we can further simplify it in a manner where we can use it, use our normal understanding of Laplace transform, etc. and etc. So if I substitute these things there, then I can write, let me complete this, I can write for fx, if I have to write df xa by du by u1 into u by u1 plus df xa by d alpha into alpha plus df xa by d delta E into delta E, that is for fx. Then I write minus mg theta cos theta 1. What was theta 1? Theta 1 is the attitude of the airplane at cruise. Okay? It is not the flight path angle. Okay? Please understand. So this is equal to mu dot. Right? And now, if I substitute the expression of dfxa by du by u1 and dfxa by d alpha and dfxa by d delta E, whatever expression I have given you, then I can straightforward write u dot equal to minus g theta cos theta 1 plus xu into u plus x alpha into alpha plus x delta E into delta E. Please be reminded that we have assumed that no thrust modeling, okay, which can be easily done the manner which we are doing for drag. Okay. And what will be the expression of xu? Xu will be, you can yourself do it. Once you substitute those expressions and once I write it, you will understand that xu is nothing but minus q1s cdu plus 2 cd1 divided by m u1. You could see that we substitute for dfxa by du1, this q minus q1 is by cdu plus 2 cd1, and then when I write u dot, so naturally u1 is absorbed here. So simply you can find out this. Once you know xu, you also know similarly x alpha will be equal to minus q1s cd alpha minus cl1 divided by m u1, and x delta E will be equal to minus q1s cd delta E by m. That's all. Okay. What is CD delta E? Don't get lost into this expression. These are mechanical. Okay. It doesn't require rocket science to derive these expressions. I have explained enough, but you should not lose the insight. What is CD delta E? CD delta E is, see, this is the airplane tail, let's say, okay, and this is the elevator. If I am flying a machine, I'll always prefer to, suppose this is my CL design. So I'll always prefer a configuration of wing, their location, tail location, the tail moment arm, all in such a way that CM versus CL should follow a trend such that here dCm by dCl is negative, restricted by the amount of static margin you are going to design, that you already know. Also, I will prefer the airplane should automatically get this configuration at delta E equal to 0. That is, for example, your main mission is to cruise, then I should be able to get a trim CL design where I need not put any delta E. Why? Because the moment I put delta E, this CD delta E tells me that there will be increase in drag. Increase in drag because you are trimming it, right? So a good designer will ensure that this trim drag, this CD delta which attributes to trim drag, should be carefully handled. Best way to do it is that for the most of the operation which you want to fly the airplane, make sure it is trimmable with delta E equal to 0 or very, very low, right? That is why CD delta is also an important parameter. And then another important thing you should understand, the CD delta E or CD and CL, then you will find CL alpha, you will find CM alpha will be coming, etc. These are non-dimensional derivatives. They don't have any dimension. But if you see all this, XU, X alpha, X delta E, they all have dimensions. For example, the dimension of XU, you will find it is second inverse. Dimension of X alpha, you will find fit second by 2. Forgive me, I am using fit here. Similarly, X delta E, you will find it is having a dimension. So this XU, X alpha, X delta E, they are termed as dimensional stability derivatives. You will soon realize these dimensional derivatives XU, X alpha, X delta E, similarly like MU, M alpha, M delta E, ZU, Z alpha, Z delta E, all will play important role in deciding the dynamic stability of the airplane. So these are termed as dimensional stability derivatives. Okay. So this is the example of how to simplify the equation in a convenient form for our further analysis. I have demonstrated it for first equation Fx, which is u dot equal to this plus x delta into delta E. Similarly, or similar exercise I will do for Fz, then I can show that once I try to pick Fz minus mg theta cos theta 1, oh no, this is not cos, mg theta sin theta 1 is equal to m w dot minus q u1. If I pick the second equation, and I know again Fz will be function of u by u1, alpha will be alpha dot, qc by 2 u1 and delta E. Then I can write Fz as df Za by du by u1 into u by u1 plus df Za by d alpha into alpha plus df ZA by D alpha, alpha dot, we will non-dimensionalize this. So, we say D alpha dot C by 2 U1 into alpha dot C by 2 U1 plus DF ZA DQC by 2 U1 into QC by 2 U1 plus DF ZA plus D delta E into delta E. Okay? So, what is the next step? We have already learned when we handle the fx equation, we have to substitute the expression derived for this, this and this at steady state. Already those expressions we have identified and derived. We substitute those here and then put it here and complete this equation. And once you do that, you will get W dot minus U1Q is equal to minus G theta sin theta 1 plus ZU into U plus Z alpha into alpha plus Z alpha dot into alpha dot plus Z Q into Q plus Z delta E into delta E. Okay? And what will be the expression for ZU? Minus Q1 S CLU plus 2CL1 divided by MU1, then Z alpha will be equal to minus Q1 S CL alpha plus CD1 divided by M U1. Z alpha dot will be given as minus Q1 S CL alpha dot C bar by 2M U1, and ZQ will be equal to minus Q1 S CLQ C bar by 2M U1. Please understand that we have already derived the expression for CL alpha dot, CLQ. So, these things are just algebraic manipulation. What we have done, we have expanded FZ, substituted those expressions, then divided by MU1, and we got this equation. This is what we are looking for. So, this is my second equation, and also please understand that as XU, X alpha, X delta E, ZU, Z alpha dot, ZQ, Z delta E, they are all dimensional stability derivatives. Okay? You can check their dimension, they have a finite dimension. Similarly, for M, if I come for M, we will get equation of the form. For M, we will write, you know that M equal to I Q dot. So, I can write Q dot equal to M divided by I, and again for M, I will write dm by du by u1 into u by u1 plus dm by d alpha into alpha plus dm by d alpha dot c by 2 u1 into alpha dot c by 2 u1 plus dm by d qc by 2 u1 into qc by 2 u1 plus dm by d delta E into delta E. Of course, by now you are expert that these derivatives, partial derivatives, to be evaluated at steady state. And we have all done this. We know this expression. And if I again substitute it here for M I put this and divide by I by y. So, I will get equation of the form q dot equal to m u into u plus m alpha into alpha plus m alpha dot into alpha dot plus m q into q plus m delta E into delta E. And you could check yourself, the expression for mu will be, if I write it here, expression of mu would be given as q1 s c bar cmu plus 2 cm1 by I y u1, then m alpha would be equal to q1 s c bar cm alpha by I y, then comes what? M alpha dot. M alpha dot would be equal to q1 s c square cm alpha dot by 2 I y u1 mq will be given as q1 sc square cm q by 2 I y u1, and then m delta E will be equal to q1 s c bar cm delta E by I y. Okay. Now, let us see here, try to understand these dimensional stability derivatives. If I pick m alpha, you could see it has Cm alpha. What was Cm alpha? Cm alpha was dCm by d alpha, and we have realized that Cm alpha has to be negative for ensuring static stability of the airplane. And what is the dimension of Cm alpha? It is a dimensionless, right. So, these are dimensionless parameters, derivatives. Okay. However, what happens to m alpha? You could see it is no more dimensionless, it has a dimension. Okay. To be more precise, if you want to know the dimension, this will be, you can check yourself of this dimension. So, what again you could see this m alpha dot mq, mu all are dimensional stability derivatives. This was non-dimensional stability derivatives because they attribute to stability. Okay. So, this should be very clear in your mind before we do some jugglery here and there. Our life needs some rest because so much of expressions we are deriving, and we need to know what we are going to do with all this. The big question will come whether this approach is helping us or not.